Hi, today we're solving problem 46. It was proposed by Christian Goldbach that every odd composite number can be written as the sum of a prime and twice a square. So here we're given 9, which is the first odd composite, which is 7, the prime, plus 2 times 1 squared, which is twice a square. And then we're given a bunch of examples of that for odd composite numbers. It turns out that this conjecture was false. We need to find the smallest odd composite which breaks this proposal, which cannot be written as the sum of a prime and twice a square. The approach we're going to take for this is generating prime numbers, generating doubles of square numbers, and going over all odd composite numbers until we find a value which cannot be written like this. So when we're given a number, we can go over all prime numbers, and given a prime number, we can check if the remaining part is in that double square set. So we can go ahead and implement this. Now the first thing we need to do is set a search limit, but we don't know where this number is going to fall. So what I'm going to do instead is I'm going to set a val answer, and I'm going to create an iterator that starts from 1. And the values in this iterator are going to represent 10 raised to what is our search limit. So I'm going to flatMap here. So given my index, I can set a search limit to 10 raised to that power. So what we're doing here is we're taking the number we're currently at, and then we'll have search limit starting at 10, then 100, then 1,000, 10,000, and so on. And what this function passed to flatMap is going to return is an optional value of the first odd composite, which does not satisfy the proposal. So we're going to give an option here, and if it does exist, the new iterator we get from this will return that value. Otherwise, the original iterator will go to the next value and we'll search again. So given a search limit, we have a few things we need to calculate, the first of which is all of the primes underneath that limit. So here in the util object, I've copied the sieve of Eratosthenes, which we've seen in previous videos, and we're going to use that here. So I'm going to create a val all primes, and I just do util.sieve up to the search limit. Now, as I mentioned when we first looked at the problem, when we're looking at an odd composite number, the way we're going to check for cases like this that'll work is we're going to go over all prime numbers. But we don't want to go over all prime numbers. We only need to go up to the prime numbers that are less than the number we're currently looking at. But sieve returns us a set of integer, and we can't guarantee ordering there. So we can't use a method like takeWhile with a set. What we need is a sorted version of this value. So I'm going to create an all primes sorted. First, I'm going to convert all primes to an array so that we have ordering, and then I'm going to get a sorted version of this. So now we have a sorted array of all the primes. The second thing we need in this problem is all of the double squares. So I'm going to create val double squares. We're going to first start out by calculating the base of each of these squares. So this is going to be between 1 and the square root of the search limit divided by 2. So this value will be our limit, because if we square this, that'll give us the search limit divided by 2, and if we double that, that'll give us our search limit. And that's what we're doing here. We first square and then double it. So the last value will be the last double square less than the search limit, because here we're going to convert this to an int to round it down. Now, given one of these values, we want to get a double square, so I'm going to take the number and do 2 times the number times the number. And this will give us a double square. So here we have an index sequence of int for our double squares, and I'm actually going to convert this to a set because we're going to be looking, as we iterate over primes, given a number that we need to find a way to express as the prime and double square, we're going to first take a look at one of the primes, and then we're going to say, is the remaining a double square? And we can just check within this double squares set if it's there. And set is a lot faster checking if an element is there than an index sequence. So now that we have all of this set, we can go ahead and implement our search. The first odd composite number is 9, so I'm going to start with that. I'm going to go all the way up to the search limit, and I'm going to go by 2 because we want only odd numbers. Now the second thing we have to remember is we don't want just odd numbers, we need odd composite numbers. And a composite number is a number that's not prime, so I'm going to filter not the ones that are in all primes. So I'm going to pass all primes dot contains as a function here. So it's going to check, oh, does primes contain this? If it does, I don't want it. Now for all the remaining odd composite numbers, I need to find a number such that there exists a prime where the remaining is a double square. Now to iterate over the primes, I'm going to use all primes sorted here. I'm going to do a takeWhile. So I'm going to keep on taking in values until we find a value that's greater than n. So I'm going to take while the number is less than n. So as soon as we find a value that's equal to or greater than n, we don't want that anymore because we won't find another value that would be a double square with that prime, so we don't want any values past that. And we know that all values past the value that we get here will be greater than the value we already checked because all prime sorted is sorted. Now, given an all prime, we need to see all these primes, we need to see if there exists a prime such that there is a corresponding double square for it. So we need to find a prime such that double squares contains n minus the prime, because that's the remaining part. We take our number, we subtract our prime, we get the double square. And if double square contains it, we'll return true. This will return true, and we'll have found a number. So we're done implementing the search for every single search limit, and doing this flat map with this returning an option is going to give us an iterator of all of the values, but they won't be calculated immediately, they'll be calculated lazily. And we only care about the first value, so we're going to call the next method on our iterator, which gives us the next element from it. Now that we've gotten our answer, we can print it, and we can run. So we can run. And we've got a 9. Now let's take a look at what went wrong with our search. Now why did we find 9 to be an odd composite? Because here we see we have 7 and 2 plus 1 squared. Now what are we doing here? We're looking for one that cannot be expressed. Oh, I know exactly what I've done. What I've done is here I'm checking, does there exist a way to express it? We want to find a number such that it cannot be expressed. So I'm just going to put a not there at the beginning, and then we'll be looking for all of the cases where we can't express it. Now we can run, and we get our answer. That's it for problem 46. I'll see you next time when we solve problem 47.